So now we want to approximate that same integral with a right-hand rule. So that's the integral from 0 to 1 of e to the negative x squared dx. And if we're going to do this with a right-hand rule, that means with n equal 2, we're going to have two bases. So our delta x here is still going to be delta x is still going to be 1 minus 0 b minus a over n, so 1 minus 0 over 2, which is 0.5. So that first base goes from 0 to 0.5, and the second base goes from 0.5 out to 1. If we're using the right-hand rule, we're going to get our height from the right-hand endpoint of the base. So our two approximating rectangles are going to look like this. Here's our first one, and then our second one, we're going up from the right to the graph to get the height. It's going to look like that. See, if we go to our sine example here with Wolfram demonstration, here's the left sum. So we're using the left side of each base to get the height of the rectangle. If we look at a right sum, this is for sine x. Now we're using the right side for this first base. Use the right side to get the height. For this base, the right side gives the height of the rectangle. Right side up here, height of the rectangle. And for this base at 2, right-hand endpoint gives the height of the rectangle. Notice that sum is 1.61, which is bigger than the actual area of 1.41. So here we can estimate this integral as we can factor out that common base and then just add up the function values. Again, this is height times base plus height times base plus height times base all the way for all the rectangles. Here we only have two. So our base on the outside, 0.5. And then on the inside, sum of the two heights. So the height here, going over and across, looks like it's about 0.77. And then the height here at 1, go up and across. So that looks like that's about halfway between 0.25 and 0.5, 0.375. Approximate. So let's go ahead and enter that in the calculator. So we have a 0.5 parentheses, and we've got 0.77 plus 0.375. Close up our parentheses, enter. 0.5725. So that's graphically. Or if we want to do this algebraically, then we would actually plug those values into our function. So this will be approximately the 0.5, which is our delta x. And then f at our first value, that's going to be f at 0.5 plus f at our second value, f at 1. And so this will be 0.5 here. And then our function plug in 0.5, so that's going to be e to the negative of 0.5 squared plus, and then f plug in 1, e to the negative of 1 squared, just e to the negative 1. Remember this, you take the power before you do the negative sign here. So let's see here. Let's go ahead and compute. So that's a calculation like this. We just have to change our 0 to 0.5 and our 0.5 to a 1. So let's see if I can get a 0.5 here. We got parenthesis. If we didn't have anything in between, we could just do second enter and bring that back up again. But second of ln and then negative 0.5. That gets squared, arrow, plus second of ln is our e, and then negative of 1 squared is just negative of 1, right? Close our parentheses up, 0.5733 to 4 decimal places. And then as you add more rectangles, your approximation is going to get better. So here we had 4 rectangles. If we take this slider to the right, well, first of all, here our error in the approximation with 4 rectangles. Here's error. It's that lighter area there. There's error. That's overshoot error. And then undershoot error. So a little bit of canceling that goes on. But what happens here when we increase the number of rectangles, say up to 20? We can see that our error values here are much smaller, and our approximation of 1.46 a lot closer to the exact value of 1.416. And in fact, as you take more and more rectangles, error goes to 0. So we're just looking at a very simple case where n equals 2.